All right, good afternoon. That sounds good. Tom, for the moment, we've got you just muted because we are having some feedback issues. I'm going to give the introduction, then we're going to mute here in Silver Spring and then unmute you. Seems that that should work. So welcome everyone for this edition of the Virtual Lab Forum, coming live from the Virtual Lab Forum studios here in downtown Silver Spring, Maryland. This is Steve Smith, the director of the VLab and your host for the VLab Forum, and I'm joined today with Mike Sherma, who is sitting in for John Chattel as our production manager and general logistics guy. Today we're very lucky to and privileged to have Dr. Tom Hamill, who is going to talk to us about the science behind multi-model precipitation probability in the National Blend of Models. This is a very important project in the National Weather Service. A few VLab forums ago, we heard about the science behind the everything else except the precipitation from Bruce Feenheis of MDL. And so this is a companion presentation, so to speak, on the precipitation part of this. I want to remind everyone their general format here is approximately 30 minutes of content from Dr. Hamill, and we'll follow that up with a question and answer session for the remainder of the hour. During that part, if you wish to ask a question, you can use the raise your hand feature of the GoToMeeting to indicate to Mike Sherma that you'd like to ask a question directly to Dr. Hamill, and he will unmute you, in which case you can ask your question. You can also use the chat feature through the GoToMeeting and pose a question in that manner, and Mike will read your question to Dr. Hamill. Also a reminder that this, like all the VLab Forums sessions, are recorded, and following the conclusion of this hour, we will upload that recording to the VLab Forum website so that you can share with your colleagues. So without further ado, we are going to turn it over to Tom Hamill. Go ahead, Mike.
Okay, hi, this is Tom. Can everybody hear me okay?
Yep.
Okay, well, it's always a little bit of a thrill to be called Dr. Tom Hamill. Nobody calls me that back in Boulder, so thank you. I frequently forget that I'm a doctor. So anyways, what I'm here to talk about is, as noted, National Blend of Models and how we're going to be handling precipitation or probability of non-zero precipitation in the National Blend project. I think you all have been largely brought up to speed through prior presentations. As you're aware, there's a desire by Louis Ussolini to use multi-model ensemble data from the various operational centers around the world, as well as deterministic forecasts, to provide improved guesses to the NDFD grid so that forecaster intervention is less necessary. And eventually the blend is going to cover all of the NDFD variables on the high-res grid and include an expanded set of regions, and maybe even in the slightly more distant future expand out to have more full probabilistic QPF. But for right now, our focus is going to be on intermediate lead times of 3 to 8 days and multi-model probability of non-zero precipitation. Here is an example of the sort of discontinuities that a lot of people feel subtract somewhat from the credibility of NWS products. So, you know, the forecast office in southwestern Ohio has a different vision for probability of precipitation in the Columbus area than does the WFO to their north. And you see that boundary, and that looks physically unrealistic to your eye and probably to a lot of customers' eyes. So the question is, can we make that pop product from the multi-model synthesis so skillful and so reliable that Only in the more urgent situations would forecasters feel the need to go in there and make manual grid modifications. Now, post-processing is presented with some algorithmic challenges, but it's also presented with some data challenges. Generally, the more data we can get our hands on, the better job we can do, but models are frequently changing versions, and some centers have bought into using what we call reforecasts, retrospective forecasts. Others have not. For the near term, until we have worked with NCEPT to regularly produce reforecasts for the GEFs, and until we get reforecast data from other centers under our roofs here in NOAA, we're going to assume we have short training data sets, like maybe the last 60 or 90 days of forecasts to work with. And we'll see how good we can do working with just that shorter training data set. It's our presumption that we'll be able to do half decently, as I'll show you in the coming slides, for a basic pop forecast, a relatively common just, is it precipitating or is it not? We've found in the past, though, when it comes to a 50 millimeter or 2-inch forecast, then that's really where sample size plays a bigger role. But since we're asked to concentrate on pop at the beginning, I think we have a hope of doing something with shorter training sample sizes. So the methodology that I'll outline here today is with trying to get as much as possible from that shorter training data set. Now, right off the bat, when we worked with a coarser grid resolution, this is a study that we did a couple of years ago, we had reliable forecasts from just the multi-model ensemble for at least summer to early fall, directly just using that data on a 1-degree grid. Things look nice and reliable and skillful here for a day 5 forecast. And so could we just directly use that multi-model pop without any sort of further processing? I think that there are a couple reasons to expect that as we go down to the 2.5 kilometer grid scale of the NDFD, that the answer is no. So for example, if we're making a forecast here for the Olympic Peninsula, you can see that there's a lot of detail there related to the terrain characteristics in the Olympic Peninsula. Accentuation of terrain on the windward side and decreased on the rain shadows side there. And we would like to pick up, to the extent possible, that sort of spatial detail, even if the model forecast is coarser in resolution. And that may be possible through some statistical downscaling. Another challenge is that maybe we'll have 2 ensemble members which agree upon the large-scale precipitation pattern. Here I'm showing you 5 grid boxes, and let's say the precipitation amount in 2 ensemble members is identical here. And the subgrid detail, though, doesn't agree amongst those 2 members in reality. And we would like to add some stochasticism, some randomness to the unresolved scales of motion, even if there is agreement on the resolved scales there. So that's also sort of part and parcel of the statistical downscaling which we will apply. So here's the overall methodology that we're proposing for downscaling. Let's say we're just focused on one particular model grid point, and we have a precipitation amount whose amount is just denoted by the height of the red bar. And let's say we also have a long time series of precipitation analyses for this grid point in the past. So let's find one at some date in the past that had a close precipitation amount. The closer the better. And we have the coarse resolution analysis of precipitation at the same grid scale as that ensemble member forecast. And we also have presumably a fine resolution analysis, and we can get that detail there. So The difference between the fine and the coarse resolution analysis defines a downscaling vector. That's the arrows here. And so our downscaling methodology just proposes to basically add that vector onto the original ensemble forecast. And if we repeat this process now, even if we had two ensemble members that had the same precipitation amount, if we chose different dates of past analyses, they would have different downscaling vectors that would have some predictable element to it if there was terrain-related detail, and then some stochastic element to it, just based upon the random day-to-day variations here. So we think that this is a nice way of trying to build back in some of the uncertainty as well as the predictable small-scale detail and the small scales related to terrain type forcing. Now, another challenge that I think that we can get past with a short training data set is sometimes there are systematic errors in the model. You probably have looked at many model forecasts and noticed the tendency for these forecasts to have a lot of drizzle and not as much aerial coverage of light precipitation when you actually look at observed data. So here's an example. The Canadian Center on the lower left, the Met Office on the lower right, are both forecasting for northwestern Nevada some precipitation in a climatologically very dry region. And maybe by using recent past data, we can note if the model has systematically over-forecast precipitation in that region and dry it out somewhat. So the procedure that we propose to do this sort of bias correction is called quantile mapping. And the basic idea is that you build up a CDF, a cumulative distribution function, for your forecast data from your ensemble, let's say, and from your observed or analyzed data. And if you don't see that these two distribution functions lie right over top of each other, then for a given precipitation forecast, here let's say 7 millimeters, you look up and say, oh, that's at about the 91st percentile of the forecast distribution. What's at the 91st percentile of the analyzed distribution? Well, that's a little lighter, maybe more like 6 or 5.5 millimeters. So we make that correction and adjust the raw forecast from 7 millimeters to 5.5 millimeters in such a circumstance. Now, if we're only training with the last 60 days of data, that's 60 samples to build these CDFs from, and it might not be enough. So something that we have done in our algorithm is to artificially boost the sample size at any particular location. Let's take Boulder, Colorado as an example, that sort of pentagon-shaped area in north central Colorado. And the smaller pentagon-shaped points are points where we will supplement the training data for Boulder to boost that sample size and populating the information to build those CDFs. And through that, we hope to account for that small sample size somewhat. Now, these locations have been picked off to have similar, roughly similar terrain characteristics, similar precipitation climatologies. There's only so good a job that you can really do and get a set of points that are not too close together. We would like these points to be far enough apart that they have some chance of kind of covering independent precipitation events. So there's a little bit of guesswork in the methodology for determining these supplemental data locations. And I've shown you here supplemental data locations for many other locations, for Phoenix, Arizona, for Berkeley, California, for Portland, Oregon, and so forth. And I think you could argue on the wisdom of what the automated procedure is doing for finding these supplemental locations, but our hope is that it's an improvement rather than a degradation. A last challenge, I'll illustrate this in a second, is that after we generate these pop forecasts at a high resolution, you tend to notice some speckliness to them, some small-scale detail that just happens as a consequence of processing every grid point independent from each other and coming up with a different set of past dates for downscaling and so forth. And so some smoothing seemed appropriate here, and we use a technique called a Savitsky-Gallais smoother. There's a couple hyperlinks if you're interested in a little bit more information. Cartoon-wise, here's just, let's say, an east-west cross-section of precipitation. Let's pretend it's precipitation. It's just synthetic data. The point is that if you do a simple, like, 9-point or 16-point smoother on that, that's what's shown in the middle panel, it tends to decrease the amplitude of these smaller scale maxima. And we'll like a procedure that tends to preserve those if at all possible. And the Savitsky-Gallais approach is actually a polynomial fitting approach that does tend to preserve better the high frequency wiggles there, preserve their amplitudes. Let me show you an actual example of this now. So down on the bottom panel here is just the raw multi-model pop, and on the top panel is now, after we've done our CDF-based bias correction and downscaling, and there's a little more terrain-related detail in the Northwest United States, for example. But you also see, along with that, a whole bunch of noise. And when we apply the Savitsky-Gallais smoother on top of that, that's this next one, we get rid of that noise pretty well. Now, we actually apply a weighted linear combination of that original raw, or not raw, but statistically post-processed guidance and the smoothed Savitsky-Gallais product. And that linear combination has a little less weighting towards the Savitsky-Gallais in the western United States, where some of the perceived noise might actually be terrain-related detail. But in the eastern United States, it's almost exclusively the smoothed field. So here's just sort of trying to lay it out as an algorithm here. We're going to really get most of our benefit from this multi-model ensemble, but we have two general modifications on top of that. We're doing the CDF-based bias correction to try to take out some of the systematic errors, especially at the light precipitation. And we do that statistical downscaling. So in the examples that I'll show to follow, we'll be looking at 4.5 to 5 day forecasts. We'll be looking at using CCPA, which is sort of post-processed stage 4 data from 2002 to 2013 for the statistical downscaling at 1/8 of a degree resolution here. And the overall technique is you first CDF bias correct or quantile map those forecasts. You apply the statistical downscaling. You compute a probability having downscaled each individual member, and then you smooth it. And so you can see the cumulative effect here. So the raw ensemble probabilities are shown in the blue curve. If we just do statistical downscaling without any bias correction, that's the red curve. And then the green curve is with both of those. And this is reliability, and the desirable quality is both to have something that's reliable, that lies along that x equals y line. So when you're forecasting 60%, that occurs 60% of the time, and also to be as sharp as possible. So we're issuing 0 probabilities or 100% probabilities as often as is feasible to do so. And so you see an improvement in reliability, and then summarized in skill of pop, an improvement of the pop skill score as well. I will mention that actually the raw data here, flipping back and forth, you see the raw forecast is 38% skill. That really wasn't an improvement over the raw ECMWF forecast. The big improvement that I think NCEP gets is largely coming from ECMWF, if we can include that in the system. And as I understand, there are negotiations still ongoing with ECMWF to allow us to use that in the blend product. And I'm not sure the latest status of this. Maybe somebody at MDL might know a little bit more about the latest than I do. We could discuss that in the Q&A period. Okay, so just quickly a case study here. This is a very ordinary day, nothing particularly special. I'm just showing you first here 4 panels of ensemble mean from the 4 different centers. We'll actually probably exclude the Met Office in at least the version 1 of the blend, but it's included here for grins. And then the deterministic forecasts from the 4 centers. And finally here, the pop from the raw ensemble system for each of the 4 forecast systems. And I'm asking you to sort of concentrate on that area in southern Colorado, northern New Mexico here, where you can see each of the systems has pops in the 50% or above range. So when you actually see what happened on that date, that's the next slide, the precipitation analysis in the upper left, nothing actually happened there. And the raw multi-model, upper right-hand panel, was having probabilities in that 50% and above range in that area. And the downscaling itself didn't really tend to touch that. That's what's shown in the lower left-hand panel. But that combination of downscaling plus the bias correction, which tamps down that tendency to over-forecast light precipitation amounts, while it doesn't take probabilities down to 0, in that region it at least decreases them down to more of a 20% nuisance level that I would hope and trust is maybe giving forecasters a little more of a signal that, it's not a sure thing that precipitation is going to happen. Now, one of my concerns kind of for the long term, not for the short term, but as we head forward to the NDFD providing guidance for not just POP, but for here larger events, 10 millimeters, but maybe also in the future 2 inches, 4 inches, whatever. Can the same system reliably produce improved guidance, or do we need something else? And in the case here, looking at 10 millimeters, from the raw to the downscale to the bias corrected, there really wasn't much value added from these extra machinations that we added on top of things here. So we think we're going to need to use more advanced methodologies for version 2, 3, and beyond, possibly. And we'll need especially bigger training data sets here. So I'd like to kind of discuss where we're headed in the longer term here. There is a program, I've been involved in a meeting the last couple days on this program. It's called NGGPS, and I have the ability to try to steer some priorities related to post-processing. And one of my priorities that our post-processing team is in agreement on is that we would like regular generation of reanalyses and reforecast data sets to provide these large training sample sizes, as well as the development of the advanced post-processing methods. So where are we with this? We have an existing reforecast for the current GEFS system, but in September that's going to be upgraded to a new system. We don't have a new reanalysis in place right now, but we have been funded to start work on a next generation reanalysis, and we'll be jump-starting that and then working hand in hand with EMC and Climate Prediction Center in 2016 to generate that. Once that reanalysis is generated, then a reforecast will be straightforward. So our hope is 2 to 3 years hence we'll have a next generation reforecast, and we'll have also set up the procedures in a way that allow us to do this much more frequently in the future, that it won't be sort of a one-off that's done every 5 to 10 years, but is done regularly every 2 years or so. In terms of advanced post-processing methods, I've had the pleasure of having a colleague named Michael Scheurer join our staff, and he has developed distribution fitting approaches here that have provided an improvement over some of the methods that we have been working on. The technique that he uses is called a censored shifted gamma distribution. A gamma distribution has got the attractive ability to sort of change its shape based upon whether the precipitation is light or heavy. One of the problems that we have with such distributions, though, is that we have a mixture with precipitation of a finite event, zero amount, that has a probability mass and otherwise is a probability distribution. And Michael has developed a technique that involves shifting a gamma distribution to below zero values and then counting the area that is below zero as the probability of zero precipitation. And in this way, he can account for that mixed nature of discrete and a continuous distribution. On the next slide, this is an example of how that distribution fit might change with different ensemble mean precipitation amounts. So at a very light precipitation amount, that distribution tends to be exponential in character and have a high probability of zero precipitation. That's the gray area sort of now on the horizontal scale. And as you move to 10 and then 25 millimeters, it tends to look more Gaussian. He's also developed a way to incorporate not just the ensemble mean, but spread information from the ensemble so that the distribution broadens out as there is more uncertainty. So this is a comparison against a technique which you may have seen me present somewhere along the line, an analog technique using our reforecasts, and Michael's more recent censored shifted gamma distribution. Let's just focus on the right-hand panels. This is the skill as a function of lead time. That's the different color curves, and time of year. That's along the x-axis. For our older analog technique, and then the newer censored shifted gamma distribution, CSGD. And just focus on, let's say, the one-day forecast up top from our older analog technique. In the wintertime has got maybe 17% probability. And the new CSGD forecast for a two-day forecast has got relatively, or even a three-day forecast has got comparable skill to that one-day forecast. So for the high precipitation events, there's been an addition of significant skill through this distribution fitting approach. So this is something that we're interested in getting into operations. The forecasts are reliable. Up top, again, analog, below the shifted censored gamma distributions. And they tend to be attractively sharp, sharp in the sense of meaning issuing high probabilities more often. So here's a case actually where this was an atmospheric rivers case in the northwest U.S. Mount Rainier got lots and lots of trees blown down, and there was closure of Rainier National Park because of this event. In this case, actually, the raw ensemble did a very good job, but that's not always the case. Our analog forecast for over an inch of rainfall in a 12-hour period, was in the range of 80% or so here. But with the shifted censored gamma distribution, it was more in the 90 to 100%, really giving you that added confidence that a big event was coming here. And this is a general characteristic which you tend to see repeated across other high-impact events. It just generally produces higher probabilities and still maintains some decent reliability of the forecasts. Now, could we use this with a shorter training data set? Here, we've looked at the amount of degradation of skill for shorter lead forecasts up top, longer lead forecasts down below, again, as a function of time of year. For decreasing the training sample size to either 3 years or 1 year, And in the case of when we have 1 year of data, we also examine what would happen if we didn't just use every grid point, and we didn't just use Portland, Oregon, but we supplemented data from other locations around Portland in that training process. And it actually looks like with 1 year and supplemental data, there is a degradation of skill compared to using the full 2002 to 14 training data set, but it's a drop-off in the 2% range. It's not a wild drop-off here. And this gives us a sense that this might be a suitable technology for applying downstream, even with relatively modest training data sets here. So this is an area that we're envisioning being sort of a follow-on for the technology that I described earlier with this quantile mapping and statistical downscaling. This might end up being a replacement for that down the road. And when we do have the full reforecast data in place, we hope and expect, we'll have something even better. So, conclusions and next steps. Our proposed procedure here with this quantile mapping and downscaling does seem to improve POP. We are working on more advanced methods as shown, and also note that this is being evaluated in real time by forecasters. So apologies for not including the hyperlink to the site that you can go to evaluate them, but these are being produced and looked at now. And maybe some of you have had the opportunity to look at them, and I'm eager to hear if you have what you have noticed or not noticed in these products. So with that, I guess let me open my little control panel up here, and I'll be happy to take questions or comments.
Okay, thanks. Mute Tom. Okay, so Tom, we're gonna, because we're getting this feedback problem, we're gonna have to be careful and switching muting and unmuting. So I'm gonna try to ask the question, then we'll mute locally and then unmute you so that we avoid that. But first, Mike, so do we have anyone on the go-to who has posed questions so far?
No raised hands or questions down here.
Okay. So I'll start off here in the room, and then here in MDL we'll probably have some other questions. So first one, Tom, is in regards to what you presented here and the idea of going to shorter models like the HER and in the shorter time frames. Can you apply this methodology to including shorter projection ensembles, and if not, what are your thoughts on that?
Unmuted.
Okay, thank you. The methodology that I described, I think, is one that you could blend in the HER information together with the global ensembles with, let's say, the censored shifter gamma distribution. I suppose if you have, let's say, the last 60 days of data, you could probably do well. That's what our results with global models seems to indicate. And I don't have any reason to believe that qualitatively it would be any different if the HER information were included. So our hope is that we've developed something that is somewhat agnostic to your choice of models here.
Okay, thank you. Do we have a question in the room?
A question from a written question.
Okay, go ahead.
A question from the viewers. Why is the high rainfalls not well predicted by the CDP correlation. This is very nice work. Actually, it's the next thing. So why is high rainfalls or the high rainfalls not well predicted by the CDP correlation? Tom will unmute you momentarily here. Okay, you're being unmuted now.
Unmuted.
Okay, yeah, thank you for that question. It's actually a pretty straightforward thing, and I often throw a slide in there to sort of explain that. But let's say, you live out in the western United States, a place like Boulder, where we often have dry periods that can last for a month at a time, and then a heavy rainstorm comes and gets you for a day. Well, in such a situation, Boulder, looking back, does not have many samples of other heavy rainstorms to work with. So if you're trying to make some guess as to how to correct today's 25 millimeter forecast, what you really want are other samples of 25 millimeter forecasts in the past. If they're not available at Boulder, well, you might pick up a 25 millimeter forecast from Grand Junction, Colorado, but it could have a very different climatology and systematic bias in the GFS system or the ECMWF system. So that's why the sort of easiest thing for us post-processors is just to have a longer training sample size, so we could look back into the case, and if it is forecast 25 millimeters in Boulder today, if we have 20 years of data, we'll have enough of a sample size of other 25 millimeter events to figure out if it's systematically over or under forecasting and make those corrections intelligently. So that's the essence of why we didn't really get too much value from applying the methodology that we had that worked for POP, but getting a good result for higher precipitation amounts. It's that fundamental limitation of a small sample size.
Dan Melendez asked.
That's the one we did.
Yeah, is that the one we just did? Okay, so he's responding to it, I guess. So in what areas there should not be a problem is what I think the response is to the question. I think, I don't know.
Okay.
Yeah.
All right. Other questions? Is anyone using the raise your hand feature have a question?
There we go. Yeah, Dan Melendez.
Okay.
Dan, we just unmuted you, so do you want to ask your question over the phone?
Thank you. Tom, can you hear me? Hello?
We have Tom muted.
Yeah,
Hang on a
Tom.
second.
Yeah, hang on. Okay.
Yeah.
Okay.
I can hear you.
Can you hear me? Hello?
Go ahead, Daniel.
Okay.
Yes, I can hear you.
Thank you. So I just wanted to understand that this problem of the high rainfall was just specific to the dry areas. In wetter areas, you would not expect that to be a problem. Is that correct?
Unmuted.
So it really depends upon how wet you're talking about. If you're talking about the Olympic Peninsula, where a 25 millimeter event might occur every week or more in the wet season, then indeed, you probably have a decent sample size unless it's a very unusual winter like the last winter was. But I don't mean to imply by giving that example of Boulder, Colorado, that small sample sizes are a problem that are only of concern in the western United States. If you are in Washington, D.C., it still is pretty unlikely that you have had many 25 millimeter events in the last few months, not enough to intelligently judge whether the model is systematically over or under forecasting. Now maybe you take Washington, D.C., the terrain's a little more homogeneous around there, so you might supplement that data from other points on the East Coast and have enough of a sense of whether the model is under or over forecasting. And that's, again, kind of the underlying rationale of using these supplemental data locations. So I think there's always a desire for a greater sample size for those of us to do post-processing, but we do try to play these tricks and games of doing things like using supplemental training data locations, which tend to work better in regions with more homogeneous climate characteristics, like here on the East Coast, than they do in the Western United States.
All right, Tom. Thanks. This is Steve Smith. I got a follow-up question, kind of general. So I believe you've touched upon this implicitly in your talk, but I'd like you to expand upon it if you could. So in a blended approach, an ensemble approach, there is a risk that your ability to forecast extreme events is muted or suppressed or otherwise curtailed, and so obviously those are the big ones that we worry about. These are the ones that really are drivers for Weather Service decision support. So either in what you already presented or just in other ideas, how do you think what is the leading edge approaches to try to bring those out or preserve those high-end events in this type of a system?
Unmuted.
Okay, I think that the easiest way for me to talk to that one is actually to show my screen again. I don't know if it's still, if you still can do that. I'm going to go.
We'll put your screen back up.
I'm going to pull up a proposal that I had submitted here and show a figure that I think is how I would prefer to go about trying to deal with that problem. So this is a proposal we submitted to USWRP. It got turned down, but you know how these things work. You go to the next funding agency and have luck. So can folks see my screen okay?
Yes.
Okay, in this figure here, let's pretend that the left-hand panel is the amplitude is a precipitation event, and that precipitation event varies in its magnitude as well as its spatial location. As you just mentioned, the ensemble mean, which is shown by that heavy dashed curve, ends up being lower in amplitude than pretty much all of the members. And that's a consequence of the fact that the members disagree somewhat in the positions, and so that ensemble averaging gives you something which doesn't sort of reflect the spatial characteristics of any of the particular ensemble members. So one thing that might be possible is to shift all of the ensemble members in some way towards like a coherent center of gravity, the central solution that represents the most likely position of all of those. And that's what's shown on the right-hand panel. And then when you take the ensemble mean after this shifting, then you have preserved a lot of the amplitude. You end up with an average, but an average that reflects really the no longer the spatial uncertainty, just the amplitude uncertainty. So this is where I would like to go with this. We're still trying to rustle up the money to do this sort of procedure. There's actually a fairly rich literature in this sort of thing. If you were to Google the terms field alignment or feature calibration and alignment, you would come across literature where this has been done with things like 500 millibar height fields and such. So I'm showing you a toy 1D example, but this could be applied to a gridded field here. And we hope and expect to give better results. So that's the approach that I hope to be able to pursue in the future for this.
Okay, thank you very much. Appreciate it.
Okay, well, you're welcome. Any more questions?
Just, we're checking. Hold on a second. All right, Tom. I think we're good. You want to mute him up again?
Yeah.
Okay. So thanks, Tom. Really appreciate this follow-up and filling in the the website of the blend, so to speak, and your efforts here to do that. I apologize for the, we've got a new telecom system, and we need to work out some of the bugs here, but I would remind everyone the presentation will be uploaded to the VLab website, VLab Form website after this, so you can listen in again to Tom's talk. You can also check out the slides that he has provided, as well as quite a number of supplemental slides that elaborate on what he presented in his core content. Just to remind folks that coming up in August, in our VLab Forum on August 19th, we're going to have a precipitation by Joshua Sheck of Central Region, who's going to speak about the Extreme Precipitation Forecast Improvement Project. So that one is obviously quite related to what we've heard today, so I encourage folks to join us for that as well. And then not in later on in the year, in December, we've already booked Joshua and Paul Kirkwood to talk about another research operations project, the Damage Path Toolkit. And for that, I think that about wraps it up. So I want to thank everyone, and we will see you in August.